guys have got the material for the last class computer architecture.
Yes, sir.
Yes, sir.
Okay, so let's start from today. I'll be mostly taking over from it'll be from my side. So let's start over. Today's class, what we will do is we will I'll start. So how do I 0? So if it is 1, it is going to be B. How do you represent this particular? How do you explain this? A is equal to 0, B equal to 1, and something is equal to 1 means B bar. And schematics. Any doubts until now? Where what are the outputs? Correct. Correct. That's all. As of now, for implementing the half adder, these are the things that you have to declare. So here, if you see the inputs are A and B, the output is going to be sum and carry. So how do you write a Verilog code? So in Verilog code, we define the hardware as module half adder, and you can declare all the inputs and outputs that are required, input and output variable inside this parenthesis. A comma B comma sum comma carry. Then you can say among these which are inputs. You can say input. Do I go back? One minute. One minute. I missed my this board response somewhere. Yeah. Okay. So it is going to. Okay, so let me start. So it is going to be module half adder. Sorry guys, this there's some issue with my tab. It's took some time. Sorry. Module half adder, and you have A comma B comma sum comma carry, and you have input. Inputs are what? It is B, and then you have output sum, and you have output carry. So these, in Verilog, you will have to end everything using a semicolon. So you can as well comment also saying that this is my input. So this I should be small. So everything in lowercase. Okay. So it is going to be input for A. Like this, you can comment. This is meant for commenting. And then you have so Verilog, yeah, in Verilog you have different ways of writing the operation. One is either you can use a structural method. Structural method is nothing but the schematic that you have. This is the schematic that you have, which is going to be A XOR B and A into B. Sum and carry. So structural is nothing but you are going that is happening in the writing using a using the gates expression name itself. For example, in Verilog you can write XOR. This means the XOR operation, and for this gate, for this XOR gate, you are going to name as say gate underscore XOR. So this is going to be the gate name. This is the XOR gate, and this is going to be the gate name for the gate name. Is this is the name that you are going to use for this particular XOR. If you have say another XOR in the circuit, you are going to name it as gate underscore XOR underscore 1. So this is the name for the gate. And what is the operation? You know, sum is equal to A XOR B. Sorry, A bar B plus A B bar. So here, if you have, you can just give the inputs and outputs alone. So first you have to say the output, which is going to be S and A comma B. So this is the basic structural flow. This way, whatever I'm writing is called as a structural method. I write it here. So this is going to be the structural method. Then you have AND operation. This is the AND gate, and the name for this AND gate is going to be gate underscore AND, which is going to be C comma A comma B. Then that's all. Since you started with a module here, you're going to end the module here. End module. So this is the structural method, structural representation, structural Verilog code representation for adder. Similarly, you have another called as data flow representation. So how do you do in data flow representation is same thing. Same, you will have to say from module to output, everything will be same. So I'll repeat here. Module half adder. A comma B comma sum comma carry. You have input. Oh, sorry, this is going to be small a b sum and carry. Yeah, a b. Mod input A, input B, output. You can as well write like this S comma C also. Output sum and carry. Then you this is going to be data flow representation. So data flow will have this. So there is a keyword called assign in Verilog, which is assign. S is equal to A XOR B. This is the data flow representation for sum, and you have assign C equal to A and B. Then you have end module. So this is the data flow representation. You're able to see the screen, what I'm writing?
Yes. One question, sir.
Yes, sir. Yeah.
Maybe so that is a combination of both, right? Where will we combine? These are now individually they are declared, right? In data flow and structural flow, right? ARB and ANB, XRB and ANB, correct? So the overall circuit is a combination of XRB and XRB plus this one ANB, correct?
So yeah, the circuit will have two inputs and two outputs.
Okay.
So you are able to see in the circuit it has two inputs and two outputs.
Okay. And how are these two leveraged? Structural one, how it is leveraged, and data one, then it will be leveraged at hardware level. Are these two?
Both are going to get translated into same hardware only. But it is the convenience only. It is users' convenience. Whichever you prefer, you can choose.
Okay, so user convenience. So we can use any of these things.
Any of the things you can use, either structural, you can use data flow or behavioral. But that is actually not the that is the answer that I can give in for this class. But if you ask me, out of my experience, it is nobody is going to use structural or data flow. It is going to be behavioral flow. That is which I'm going to tell you now. Because behavioral flow will be something like you have to just say the behavior of the circuit, and that saves a lot of time in writing the code. But if you see structural data flow for simple circuit like this half adder and simple circuits which are like 10 logic gates are there, for those things and all, it will be easy. For if you have millions of gates, in that time even behavioral representation will be like very tedious. That's when we started using BlueSpec, which I was saying, like in IT we use BlueSpec.
Yes, you are saying people are working. Okay.
So Smita has a doubt. Could you please provide some insight on when FSMs will come into picture? Okay, so FSM is when, so once we complete this combinational thing, we'll go to sequential, and after sequential we'll come to FSM. FSM will be giving you only a very brief explanation about finite state machines. How do you write Verilog code on those things and all. We'll come to that.
So any of these two codes, right, these are compiled and these were interpreted, like how it will be. So what is the flow of the execution of this code?
So this code will have to, so there are compilers for this Verilog compiler available.
Okay.
There are open source compilers also available for if you're using Linux. It's called Verilator, that is available. You can write this code and you can compile.
Okay.
So for compiling, you need something called as a test bench.
Test bench. Okay.
Yeah, test bench is where you pass inputs to the to the input pin A and B, and observe the output at S and C, the sum and carry.
Okay.
So if with that you can confirm that your circuit is behaving according to your requirement or not.
Okay. Okay. And okay. So once it is compiled, like to what language this will be converted into assembly language or? No.
Now we are not going to that. That's Professor Gopal's board. We are not going to
that. Okay.
We are not going to that. So this after you write Verilog, we will go to, as someone said in the chat, I think Anirudh said, we will be taking to synthesis. Okay. Synthesis is where like it is going to be we are going to take this design to a fab for fabrication.
Okay.
So we will go into that. So this is completely chip design, not once the chip has come, whatever you are saying, that will come into picture.
Okay, once the chip has come. Okay.
Yeah.
Okay. I mean, just correlating, sir. I mean, how this will translate actually. Okay.
Fine. Okay. Fine. So this is going to be I have told data flow representation, and for behavioral, it is going to be like this. Until this, it is going to be same. After this, I'm writing. So only this part will change. What is going to be changing is it will be like always statement will come, always at the rate of any inputs. If you put star, if any input is available, begin S equal to A XOR B, carry is equal to A into B, A and B, and end module. So this end is going to be for this begin that you have written, begin end and then end module. So this is for behavioral representation. Okay, so let's quickly wrap this. After
so it was similar to data flow only, right?
It is similar to data flow, but here you'll have suppose here you have begin and end statements, and you will say about the behavior of the circuit, which is same for data flow. Also, it is the same. Sorry, not for data flow. You're saying it is going to be data flow, behavioral. Data flow, it is going to be the same. In behavior also, it will be same, but only you will have this begin and end statements, and you also have this always at the rate of. That means if this particular things mean that if any of the input is available, either A is available or B is available, then do this operation.
Okay, sir.
So to clarify, when you do this, it becomes more like a function in C++. If you're going to make a comparison.
Yes.
And this always is like the trigger condition for it. And whenever an input change occurs, it will enter this function.
Exactly. So please go ahead.
And the begin and end will be like the curly braces that holds the the codes within that function.
Yes. Exactly. It's very similar to what you said in C.
So always at the rate, what is that symbol, sir? A?
So I always at the rate is A. This is whatever you use at Gmail, no? At the rate of Gmail.
Okay, that one. Okay. Then hash some.
Yeah.
Okay, hash begin.
Yeah. Now let's start writing a test bench for this, where this test bench is required for checking your module. So this test bench is just will act as a stimulus and pass inputs and check whether your whatever you have written that is working as per your expectation or not. So what we will have to do is you will have to again write a module for test bench. Module of adder TB, and you will have to declare registers for your inputs. Registers means for writing test bench you will have to store the whatever value you are going to send. It has to send through registers. So so let's name those registers as again we'll name the registers as what do you say D and E, reg D, reg E. So I commented here. So these are the registers. Register D, which is meant for input A, and this register E is meant for
So can't we name it A and B? It will be easier.
Yeah,
Can't we name it?
yeah, we can do that. Why I'm putting here is we will have to we are instantiating. No? We have to instantiate from there. No? So while we are instantiating, I want to explicitly show the difference. I'll come to that. If I
Okay.
name it as A and B, then for those who doesn't know what is instantiation, will be confusing. It will be confusing for them.
Okay.
Yeah. So then we will have to declare some wires for the output. That is wire F and wire G. So I'm commenting here. So this is the wire F for output S, and this is the wire G for output C. So yeah, that's all. Now we have written we have declared the registers for inputs and declared wire for the outputs. Now we will have to call our half adder module that we have written here, which is this module half adder that we have written here, into our test bench module half adder TB. This we have to call here. In the test, we are going to call the half adder module inside half adder TB. So how do we call? How do you instantiate? Basically, that is called instantiation. How do you instantiate? First, you will have to call this module name, that is half underscore adder. That you have to put here, half underscore adder. Then you have to give an instance name for this particular instantiation. Let us give it as let's look. Yeah, let us name it as half 2 as the instantiation name, half 2 underscore adder. Now in this parenthesis, what I have to put is I have to put all the inputs and output pin names of half adder. This half adder that I have written here. I have A, B, S, and C. So here A, B, S, and C are my pins. So I have dot A, then I have dot B, then I have dot S, then I have dot C. So these are the input and output pins for half adder. Now I'm going to pass values through these registers, through these input registers to A and B, and get output from S and C through this wires F and G. So that means I have to connect them. So this is the connection that I am going to do. So how do I connect? For A, I have to connect D. Dot B, I have to connect E. Dot S, I have to connect F. Dot C, I have to connect G. And everything, I hope everybody is clear on this.
So what is this names of adder rather than the instance name?
This is going to be half 2 underscore adder. This can be any name.
Any name.
Yeah, any name as you wish.
Instance name.
Instance name, yeah.
Okay.
So here I have done the connection. Now I have to pass values to this. So for passing the values, we will in test bench we use initial statements. So we use initial is basically to initialize the system. So if we do initial begin. So let's pass one value for. So my inputs are D and E. So I'm going to pass D input as 1 tick B1, which is 1 tick B1 is nothing but binary value 1 bit binary value. Then I pass for E is equal to 1 tick B1 again. Now after some say 10 cycles. So this is nothing for like this is like after some 10 time units. It can be anything. This is while writing a test bench we give some delays. What you have to do is you display the $display $display s equal to %b f. So what it will do? This will display value of output S. Similarly, for carry $display C equal to %b G display value of output C.
So percentage B is for binary.
Yeah, %b is the binary value.
Okay.
Yeah.
Then what you have declared D equal to IB1, right? IB1 and
D equal to?
You have declared, right? After beginning you have put two statements. Here in this one. After.
Yeah. So D and E are the values, right? So this value will go this value D and E value will go to this particular circuit.
Okay.
And get the value of S and F and into here.
Okay. And what are the values that you are passing? D value?
D and E are 1 1, which is going to A and B is 1 1 for half adder.
D, okay.
So D is going to be 1, E is going to be 1.
Okay.
Which in turn goes to this half adder.
Hmm.
Half adder. This input A and B is going to be 1. So which will go to the truth table. If you remember for half adder.
Yes. You have about two tables are there.
Yeah. So for sum and carry, you will get that answer. Sum will be 0, carry will be 1.
Okay, some will be, and that mathematical expression will be evaluated, right?
Yes, yes, yes.
That A XOR B plus A dot or something. Yeah.
A B bar plus A bar B.
A bar B. Yeah.
Yeah. So that's all. So here do we provide values only in binary format, or can we put some other format such as, yeah, you can use decimal, hexadecimal, anything, Smita. Here I have taken, since it's a 1-bit value, 2-bit, I've chosen binary. You can do anything.
Can you elaborate on how that declaration was made for the registers D and E, that 1 apostrophe B1?
Yeah, that's what I'm looking at.
Which one? Can you come again? Which one?
After initial begin, you declare the registers, right? D equal to 1 apostrophe B1.
Yeah.
So can you elaborate on that format?
Okay.
How it's written?
Oh, this one. Okay. So this one, right?
Yes.
Okay. So basically, what I'm putting is I'm going to pass value to this D and E, and here, since we are it is going to be 1 bit only. It is going to be, each variable is going to carry 1 bit only. A is like 1 bit, B is also 1 bit. Other 2 inputs. So I'm going to tell, I can directly say here, either I can do it like this, or I can also write it as D equal to 1, E equal to 1. So this is another representation which clearly says that it is a binary value, 1 tick B1. If suppose this is a if D is a say 2-bit number, so then I will be putting it as 2 tick B01. E is equal to 2 tick B11, like that. Or if I have to represent this in integer format, I'll directly say D equal to 1 and E equal to 3.
Okay, so the initial number is describing the number of bits that's there, and after that tick, the B represents whether it's binary or not, and then what value follows is the value of
Exactly. Yeah. Okay, so
So if it is 0, it is 1 bit B0, right, sir?
if it is,
If 0 is possible, let us say it is 1 bit B0.
oh, yeah, 1 bit B0, 1 tick B0.
1 tick B0. I mean, yeah, sorry. Yeah.
Okay, so from this, I think I have completed half adder starting from the scratch to the code now to writing the test bench also. So if you see this flow, right, we have done first we have do a block diagram, and I have understood what are the inputs and what are the outputs of a half adder is. Then we have written a truth table for that half adder. How does that half adder has to behave? Then from the truth table through K-map, we have come to a schematic circuit representation. Once we are done with the schematic circuit representation, we started writing a code. So these are the different these are the flow and different stages that an RTL comes through. Now,
Can I ask one question, sir, if you don't mind?
Please.
So this last one, right, the test bench that you have written, right?
Yeah.
It will be in the same code. Like, can you go up the functions that you have written, and it will be the behavioral function you have written. Just go up. Yeah, you have written this behavioral function, right? This behavioral representation will be there. After that, you have declared this module, right? The second one, correct?
this one.
Yeah, the module half adder TBRO.
Yeah. So this is going to be a separate code. Okay.
Mhm.
And this is the other main module is going to be a separate code.
Okay.
Now in this TB, the test bench,
Oh, okay.
you are going to call the main module that you have done here
Right.
for verification, for your functional verification.
Okay.
So you are not going to take the test bench hereafter. You are going to only take the main module after this. After, in case if you wanted to make a chip out of half adder, you will be taking the main module. You will not be taking the test bench.
Yeah, this is for testing the outputs.
Yes. So this is just a module that we are declaring. This is a format of writing a Verilog code. Once there is no inputs and outputs are available. If you see in this, I have declared all the inputs and outputs inside this parenthesis, right?
Data flow.
Yeah, in anything, data flow or behavior, anything, I have declared all the inputs and outputs in this parenthesis here.
Right.
Got it. But if in writing a test bench, I have not done that. I've just created and put a parenthesis. That's all. Sorry, semicolon. That's
It's like a main program where you call the functions. Actually.
Exactly. That's all. Yeah.
That's what you are writing.
Yeah.
Okay.
So don't we have to use end module for test bench?
I have done. I think I've not yet. Okay, sorry. So here I have to put end module.
End module. Okay.
Yes. Here should be an end statement also. End and end module.
These calls can be for behavioral function you can call, or the other two versions also can be called, right?
Yes. It is just a dependency. If you see, it is just dependent on the instance only that which you are going to use. If you are going to use, yeah.
I mean, behavioral instance you can use, or the other structural or data flow.
Yeah. Accordingly, you have to bring the pins also. .A, .B, .S, and .C. That also should be the corresponding inputs and outputs should be called here. Got it? Yeah. Okay. So this is for combinational circuit, and similarly, we have multiplexers. A multiplexer, which is very important component in circuit design. Multiplexer is nothing but you basically you have multiple inputs and one output. So for example, this is a 2:1 multiplexer, which is input 1 and input 2. Then you have a select line. Then you have the output Y. So the truth table is something like this. You have in one, in 2, and you have sum and the output. So this could be 0, 0, 0, 1, 1, 0, 1, 1. The select line is 1, 0, 0. So if the select line is 1, whatever is there in the in 1 will come out. So that means 0, 0 will come out. If the select line is 0, so whatever is there in input, select line is this particular S is there, no? This S bit. This is going to select between input 1 or input 2. If S equal to 1, it is going to choose either for this example, let's choose it as in 1. If S equal to 1, it will choose whatever values is there is in 1, it will come out at Y. If S equal to 0, that is here, if you see, if S equal to 0, whatever is there in 2 will come out 0, 1.
Okay, but how is S is calculated, sir? 1100, how did it sum?
No, I have just put simply.
Oh, you put some random values.
Random value. This table can extend. This table can extend.
I thought S is resultant of 1 and
nothing. So here if you see these 3 are input.
These 3 are input. The only what matters is the Y is what matters.
Yeah. So if these 3 are input, it is going to be something like this, like in 1, in 2, and S. So the combination will be like this: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So now you tell me what will be the out. So 0. If s equal to 1, in 1 will come out 0. Yeah, please tell me now.
S is equal to 0 means the in 1 will come, right?
Sir,
S equal
if
to 0.
S equal to 0, then in 1 should come out, right?
In 1 should come out 0.
No, I have assumed it as s equal to 1 means in 1 and s equal to 0 is in 2.
Oh, S equal to 0, then 1 will come here.
So if s equal to 0, then 1 will come out. Here s equal to 1,
0 will come out.
0 will come out.
Zero,
Like this it goes on. Okay. Now what is inside this multiplexer? Now if you take this entire truth table, okay, this entire truth table, sorry. If you take this entire truth table and then do a K-map, okay, and then drop down to an expression, then you will have a schematic circuit coming out of it. So this I give it as a small assignment to you guys. Okay, I want you guys to take it up tomorrow, if possible. Anybody is very much keen or eager can write a Verilog code until this. It is, see, this all things are available on internet, but I want something who really worked out on this and come and tell in the class. Like, it's a very simple thing. You are going to just realize the truth table through a K-map, and then here, since it is 3-bit, here it is, since it is 3-bit, it is going to be 2 to the power 3, which is 8, and then your K-map also turns to be 8 boxes. There will be 8 boxes. So please explore and come back. Let's see. I mean, who can do that? Can you volunteer now? See, that will be. See, I will note down people who are participating in this volunteer efforts, because on the certifying time, I will. On the certifying time.
We already try, sir. Already try, actually. If it's a volunteer, only one person will try.
Yeah.
Okay, let's see who brings up tomorrow. We'll see. We can choose one and let them. I choose someone. You can present and tell us, like, how does it translate to until Verilog and test bench you have to bring. It is very simple. Okay.
So according to me, for S equals to 0, the first input should be shown, like input 1 or input 2.
It can be anything. You can see it is up to you to choose which one you wanted to assume. It is nothing like, it is not like it's a thumb rule for the selection line to choose between in 1. If it is if s equal to 0, it should be in 1. If s equal to 1, it should be in 2. It is not like that. How do you write the code?
Okay, so but generally that's how it works.
Generally, it is like that. I agree. What is your name? Sorry.
Bhavya Gupta, sir.
Yeah, Bhavya Gupta, generally it is like that only. And I mean, it is not a thumb rule. That's what I'm trying to say.
Okay.
Yeah.
Sorry, sir.
Okay. So I will have to start sequential circuit, but it's just 15 minutes is there. Sorry, I missed the task. Can you repeat it once? So, Devdeep, I just said, like, you have to. So I have drawn the multiplexer. There's a 2:1 multiplexer. You can take 2:1 multiplexer or 3:1 multiplexer, anything. You will have to bring out a Verilog code by sequence, step by step, by first writing a truth table, then from truth table do a K-map out of it. Then from K-map bring a circuit, schematic circuit. Then from schematic circuit you write a Verilog code, and that Verilog code I wanted it to be completely in data flow representation, not in behavioral or structural. That's what that's my requirement. I don't want you guys to represent in behavioral or structural. Let it be in data flow, as simple as possible.
So how would we carry this out? Like, how do we like work this out on, like, here over here?
Good question. Okay, maybe you can give it as a presentation, simple presentation, or you write it down on a piece of paper and take a photo and keep it. You can present your screen and show it to us and explain.
Okay.
I mean, depends on your creativity, Robert. I have just given a problem statement. You bring out how can it be done. Let's see, like, what are different kind of solution you guys are bringing it up.
Either we can make it a presentation and we can just share it, or like we can write it, tell it, and you can write it out on the board.
Yeah, fine.
So, like, if you do for this particular problem, we can just do the simplification here itself and just what's it?
Yeah, I'm saying what I'm saying is, Rohan, whoever is going to volunteer in this, have a keep it ready. Just whatever you have, keep it ready. I may ask you to write and show you, or if you are willing to present it, you can present it, or if you are going to say through word of mouth also, you can say. But what I'm saying is, whoever is going to volunteer, be ready.
Okay, right.
Yeah, I may choose someone, and you can. I mean, whoever is interested, plus I will just randomly choose from the people who are all have done this, and they can present.
All right.
Yeah. Okay, so any doubts until now? Let's come to this topic. Any doubts until now? Any clarification other than this? Is it okay if I extend the class to 10 more minutes today? If anybody has any issues, you can tell it now itself so that we can close, or in correct time. If anybody has any issue, please raise it now itself. Because once I start sequential circuit, it will take some 10 to 15 minutes. The class might get over at 6:45.
For me, it is okay, sir.
I mean, anybody is not okay, I think that's the right question. Fine, okay. So then let's start sequential circuits. Okay, so I'll take a new board. Okay, so for sequential circuit, the main difference between a combinational and a sequential circuit is going to be that there is going to be a storage element that is going to get involved. So it's sequential circuit. You're able to see my screen, right, everyone?
Yes, sir.
Yeah. So sequential circuit looks something like this. So you have a combinational circuit. or logic. Then you have inputs, and then you have outputs. Then you have a memory. So the output is stored inside the memory, and then again, if needed, is given as stored in this memory element. If you see at a given time, you see my screen, right, everyone?
Yes, sir.
Yeah. So sequential circuit looks something like this. So you have a combinational circuit. The state voltages. Okay, zero. Okay, zero means low voltage. Low voltage. One voltage. One means high voltage. Means high voltage. Is a racing edge, or whenever there is a racing edge, or whenever there is a fail. There are two major components. One is called as a latch. There are two major components. One is called as a latch, and another is called as a D. This is 50% and 50%. That means guys, I lost my whiteboard. 1 minute. Latch as well as the clock signal is going something like this. Latch as well as the clock signal is going something like this. Your latch is. Then using that expression, then we have designed a schematic circuit, and using the circuit we have we took forward for writing the Verilog code. Now writing a Verilog code, we have seen how do you write a Verilog code. We start with declaring as a module and the module name. Then we have created inputs and outputs for the module. Then we have written the logic behind required for the module to work. Also, we have once we have written the module, we have written a test bench. The test bench will attest to the module. Will adhere. Will try to check that the functionality is met or not for the module. So through test bench, we pass inputs and observe the outputs. This is what we have seen yesterday. And later half of the class, we have come to sequential circuits. In sequential circuit, you have synchronous and asynchronous. I'll try to finish this now. So that is my intent. That was my intention.
Yeah, while doing that, I actually got to know that I have to revise.
Yes. Good. I have seen a couple of people. Yeah, good. So I wanted to pick someone new who have not spoke to me. Can we hear it from Shravani or Prudvik? Any one of them?
Hi, sir. This is Prudvik. Good morning.
Hi, Prudvik. Hi. How are you?
Yeah, fine, sir. Doing well.
Yeah. Good.
Hi, sir. This is Shravani.
Hi, Shravani. Let's hear from both of you. Please don't. Please, you can take 2 to 3 minutes each of you, so that I can cover my syllabus after that.
Okay.
Yeah. Let's start with Prudvik.
Sir, how can I share my screen here? Like, I don't
You have something on the your camera is on. You're able to see you.
So is it visible?
Yeah. Perfect.
So is it visible?
Yeah.
The complete truth table or
no, the complete truth table. Fine. What we'll do is we'll keep this last. Let me cover my portions. Otherwise, it will get delayed, and I have very less time.
Okay, sure, sir.
Yeah. Meanwhile, you guys see who can help me out in presenting this. For me, this is my first online class. I have taken multiple. You are able to, if you remember correctly, whatever you are feeding as an input, it will go and reflect it as an output there, as well as negative level trigger latch will be there. So this circuit, this timing diagram is considered the latch, and it falls down. It falls down because. Okay, let me move forward for flip-flop edge. So on the next positive edge, you see the data.
Sir, could you please clarify one thing? Like, wanted to understand the difference between clock and clock.
Yeah.
That it will continue for a period of time, right?
Latch will.
Right, not latch.
I'm saying flip-flop only.
Okay,
Sorry, not latch. I'm saying also you are observing a 1 in the data.
Yes. Yeah. At this point, it is a kind of it has come down. Not negativity, right? This one.
Your design. What actually your design design is going more some 2 to 3 codes we will see, and the test bench. There were a couple of people who were ready. Let me check.
Okay. Sorry.
Let them attention. It's not me. You are one of your classmate who is taking the presentation. We will have to encourage her. So please play.
That is 1. The input 1 is driven to the output y. So is this okay?
Yeah. Perfect. You could go on. I think we will.
Colon. That is input 1 is driven to the output. If S is low, the value after the colon input 0 is driven to the output.
Kita, yeah. So good. Anybody has having with the test bench? With the test bench, anybody has a code who can present?
A is going to be connected to so A is going to be connected to so A and A, B, and S are bits here. Groups of two. You'll see that this expression here to assign y to this. I'm not sure if this is correct, but I believe Nikita's version is more. I'll give a name for that instance mux1, and within that, a name for that instance mux1, and within that, I connect the, let's say, the pins of the, and then this end is to close off this begin expression, and this end module is used to close off the description of the mux test bench.
Perfect. So this is only for functional verification.
Thank you, sir.
Yeah.
Sir,
Yeah, Prithvi.
the one thing, sir, that in the Rohan sir PDF, the closing of end module should be one word, right? Like there is a gap between end and the module. The syntax is here, right?
Where in test bench you're saying?
Yes, sir, in test bench and as well as in the Verilog code, like design.
No, there should be only one module and one end module.
Like end module should be one word, right?
No, there is only one end module. There should not be another end module.
I'm saying the gap between end and the module. I'm not saying them.
Come again, I didn't get it.
Gap between end and the module, like closing the module, right?
Oh, there is a space you're saying?
Yes, sir. That will be syntax error, right?
Yeah. There should be, without any space, it should be end module.
Yes, sir.
Okay. Fine. See, syntax errors anyway, the compiler will tell you and will make you learn. Okay. In the main context of this class is give you the basic concepts and go ahead and try. Automatically you will learn. So yeah, good that you pointed it out, Prithvi. This is for everyone's learning. But I wanted the main agenda of this exercise is please go ahead and try your own examples. You have 1 week time. Please learn. Then on the next class, if you have any doubts, let's clear all those things. Let's make the fundamental very clear. Then we will start to climb very stronger then.
Sure, sir.
Yeah. Okay. So fine. Now we will go to FSM. Let me take my 1 minute. S2 is another state, S0 is another state, like that. And you will have inputs, you will have outputs, then you will have the condition for transition, the output of an FSM. One is the Moore machine. How from one state to another state, how why there is a change, to what state it has to go. That we can represent using a directed graph. So if you see here, as I said, here I said, right, O1 is the output for this S1 transition, and
First node or whatever, correct?
No. It didn't produce the output O1. It's not 0. The output O1 is not 0. 1 is where you have only two states. When you go when I the assessment things and all. One thing is have the assessment after the next 1 minute. I'll just get some water and then at the end of the course, the campus immersion will happen, and there you will have complete, and there you will have complete hands-on will be provided at that particular time. Now it will be going to talk to each other, which I think Arun or Satya, someone was asking yesterday on the class.
Yes, sir.
Yes, on the class.
Yes, sir.
Yeah, Satya. So I will give you a small perspective. I think the classes should also know, because see, sir, this subject VLSI, when I studied my undergrad, postgrad, and all, I from a that idea is a feasible idea. Suppose you have something, some idea where you are saying that at every 10 seconds, at every 10 milliseconds, I will have to produce an output processor, everything. This holds for everything. This example I'm saying because I have taken that as an in this class, that's why I'm mentioning. Now you have, when it goes for these will be ready. To exercise that functionality has to be done.
Okay.
So where I was.
Yeah. So it's not like that.
So where I was.
Yeah. So it's not like that. What I'm saying is for back to PCB guy, or it will go to the. Then you have hardware design team. And yeah, Satya sir, I wanted to tell you. So here, in the software parts, it is now there is a lot of requirement for.
And some I heard earlier, Prism PSOS or something was also I heard. PCB assembly, yeah, PCB assembly software, yeah.
Yes.
Without experience, they are not selected.
Hello, sir.
Yeah, 1 minute, Marufa, I'm just clarifying.
Okay, sir.
As well, point you. I mean, even we are taking internships intern. A simple internship procedure which everybody gets. At IIT, I joined as intern.
There were many concepts that were not part of the BTech curriculum. So
even I pray for you. Let's see what is happening.
Thank you, sir.
Yeah, thank you. Okay, let's conclude. I think we are going long back now. It's 10:40. from your side and see whether you are able to do the synchronous reset and D flip-flop with. Yeah, then what is it begin? It's basically
The program.
yes sir,
program.
yes sir, executed between begin and end, it will get executed.
Okay.
Between begin and end, it will get executed.
Okay. Okay.
So it,
Okay.
so it is carried out. It is carried out. As I implemented with passage on the left side, here it is clearly on the neck edge of the clock. Like here, it is clearly on the neck edge of the clock. Like just given some unit, you can give it anything. Here I'm considering as 1 nanosecond / 1 picosecond. So here, here you will have the Q as 1. Then again, here it is equal to 10 picosecond there. Here it is equal to 10 picosecond there.
Okay.
So one more thing that I wanted to tell you guys is, see, I would recommend everyone to install Linux because the entire industry for physical design, whatever you're going to work upon, runs on Linux only. You will not be able to see Windows machines. In our lab we have hundreds of machines, but none of them are Windows. We have everything Linux. I would say like you at least take up a partition from your drive and install Ubuntu at least, which is a free version of Linux. You can. How many of you are used up with Linux? How many of you have used Linux in your
currently I'm learning because I have VLSI lab in my third year right now in the university. So I'm just practicing it right now.
Great. So I would ask everyone to take great. I would ask everyone to please install Linux and start using it a little bit. Okay.
So if we take a new machine, sir, like what should be the configuration? Not only this deployment, in future we will need to install some more stuff, right?
Your normal laptop, whatever you are using, no, sir, that is itself is fine. In that itself, you can do a partition and install it.
Okay, like RAM configurations and all.
Nothing like that, sir. Your normal laptop. Yeah.
Okay.
Good, Ridvik. Yeah, good, Ridvik. Good, Nandita. So I'm going to share my screen. We'll show you. Are everyone able to see the main module that I have written? You guys are able to see? Okay. Now module picosecond. There is a $finish. That means after this end the simulation. And these are some
software for writing Verilog.
Okay, Vivado is not. Vivado is also meant. Red Hat you have to pay, right?
I guess no, sir. For a student subscription.
If it's there, then get. Okay. Just a minute.
So just a question regarding the simulator. Like I've heard about EDA Playground. Is it also worth working on?
EDA Playground has a group of software. I think it's not one single. But let me check and come back. I have not A.out. For this A. I think now it should be okay.
Yes, sir.
Yeah. So see, you are instantiating the D flip-flop here. In the test bench, you are instantiating the D flip-flop here with the instance name as DUT. Got it? Which you usually do. Yeah. So now in the waveform that I have invoked, if you see this is the test bench module, inside that there is an instance name called DUT. Got it?
Yes, sir.
Yeah. So in the so what you have to do is you have to pull all the signals from this test bench module only. You have to pull all the signals. Your D. 1 minute. You have to pull all the signals from the DUT, D, Q, clock, and reset. So I pulled all the signals. Now let me zoom out a little bit. Okay. Yeah, are you guys able to see?
Yes,
I can't zoom anymore.
Yes, sir.
So if you see here, the D signal, we are applying the reset. So reset is 1 and then the reset turns 0 here. So when the reset turns 0, then only the output will start from whatever is there in the D will come out. So in the D, you're applying the D input here. The same thing, the clock is also happening. So when you're applying the input here, when is the next positive edge? Means if you see here, this is the next positive edge. So in the next positive edge, you're able to get the Q output here. You're getting?
Sir.
Yeah. Okay. Fine. So this is the waveform for D flip-flop. Please tell me if anybody has not understood, because we will not come back to this anytime. So let me. Okay, we'll move forward then. So similarly, I have written one more code for. 1 minute. written one more code for counter. Devdeep, I'll do it for counter. Please look into that. There's another example. So same thing only I'm going to repeat for counter. Okay. Counter. So I have written a Verilog code for counter. So here if you see what is basically a counter's functionality is it has to count starting from 0, 1, 2, 3, 4, 5, 6, 7, 8 like that it has to count. So what I have made is a 4-bit counter. 0, 2, 0, then it goes to 0, 0, 0, 1, then it goes to 0, 0, 1, 0, 0, 0, 1, 1, then it goes to 0, 1, 0, 0, like that it goes to up to 1, 1, 1, 1. In binary representation, what we will do is up to, I think I need 1 minute. So in binary representation, I'll come to that. Then what we will have to do is, we are here, so becomes 0, that is gets initialized, else count is getting incremented to 1. So this always happens whenever there is a passage of the clock coming, this entire begin to end statement gets executed. So this is a counter Verilog code, and then you have the test bench. Here, the same thing, you have instantiated the counter here. So I hope you guys know you have to declare all your inputs as registers or output as wires, and then you have instantiated the counter. You have instantiated the counter here, and the instance name is DUT for this counter. Then you are doing here always #5 clock. So after 5 picosecond, the clock is getting when the clock is, so basically this means clock equal to inverter clock is basically you're generating a clock there. Begin to end. Here you're dumping a VCD for this file, and after some 20 picosecond you're applying reset as 0, then $finish after 200 picosecond. So let us run this and see. So here you are able to see only 2 files. One is the counter and another is the test bench for this counter. Then you do the compile my Verilog. So if you see there is a a.out got executed. Now you have to generate a VCD for this. Now if you see you have one more counter.vcd. Let me open it in a GTK way. Counter.vcd. So here in TD you have the DUT. Here I'm pulling all the signal, clock, count, and reset. I'm a little bit zooming out. I think you guys are able to see now here. If Ramya and all are joining from laptop, okay, you can do that. Ramya, is it visible for you?
Yes, sir. Visible.
Okay. So what you are seeing here is, so first signal is a clock signal that is getting coming. Then you see the reset. So reset is 1. When reset goes 0, then the counter starts functioning. When reset goes 0, as well as the next passage of the clock comes, then you are able to see the 1, 2, 3 goes on counting. For every clock pulse, it's getting counted. Then it goes until 9. In the hexadecimal representation, after 9 you take it as A, B, C, D, E, F. Then after that it goes to again 0, 1, 2, 3. It goes up. Any doubts here until now?
Sir, can you go back to the Verilog file for counter?
Who is it? Darshan.
It's Rohan.
Rohan. Yeah.
So for here, the declaration of inputs and outputs, why did we add the word logic before the variables?
Oh, okay. So that is also one form of representation only. You can add so this is one version of Verilog. Verilog has multiple versions. So this one version which can we can put logic also inside with that. So that is not an issue.
So the logic here is a keyword.
Yeah, logic is a keyword.
And then for count, this 3:0 is a way to initialize an array of an array, right?
Come again? For count?
The output logic count, right? This in square brackets 3:0.
That is a 4-bit counter basically.
So that's a way how we initialize an array here.
Yeah.
Okay.
So that is the array size here.
Okay. So when we're declaring array here, we'll be like from
initialization happens at line number 8.
8. No, I mean as in the declaration.
Yeah.
Declaring this as an output, right?
Yes.
So 3:0 is basically 4 bits.
So if you're going for an 8-bit array, it will be 7 colon 0.
Yes. Yeah.
Okay. Now can you go to the test bench also? So
Yeah.
in this case, this always statement, it's a different way of writing clock, right? The DFF version we use initial, and inside that we use a forever keyword.
Yes. So this is another way of generating a clock. There are multiple ways of doing it. This is one of the way. Second way is you sometimes what people will do is we will make clock as a signal, and like you have the counter, no? Similarly, they will increase for every pulse they will count clock plus 1 like that. That is also another way of generating a clock. There are a lot of ways of you can generate a clock in a test bench.
Okay.
That's all.
Yes.
1 minute, sir. Always #5 clock. There's a normal clock or any difference is there? Normal clock, #5 clock is equal to neg clock. There's a negative edges clock.
No. Here you are generating the so in the clock you have the duty cycle, right?
Okay.
So the duty cycle has positive edge and the negative edge.
Yes.
So what is positive edge is 1 and negative edge is 0.
Okay.
So to always generate 1s and 0s alternatively, you are creating the clock signal here.
Yes. Okay. And then #5 means syntax.
After 5 picosecond, this will get created. So I'll show you that waveform once again. Wait. So if you see here, this time scale, let me zoom in. So guys, you please observe here what I'm, because when I zoom out a little more, the time minutes is getting vanished away. So if you see whatever is written in the test bench for the clock, like #5, we are generating the clock. So if you see here in the top, this is the time minute: 1 nanosecond, 2 nanosecond, 3 nanosecond, 4 nanosecond. In 5th nanosecond only the clock is getting generated. That is what you are meant there. Okay. So that is what is put in the tick time scale is the keyword for assigning the time unit for that. So similarly for others also, when you're passing input also, you're giving some value, initial time value, right? So it comes with this. Okay. Anything else? Any doubt? Anything more on this? Okay. Now, so what I will recommend you guys to do is, guys, please install Linux, or if you're not going to install Linux, at least install this iVerilog and start writing codes. At least from the recording, you will have to from the recording you'll be able to see. So from this recording, you'll be able to see the codes, but still there are a lot of codes available on internet. Try to understand the code, then you can compile it and do a simulation, see the waveform. So this in the upcoming week, if you are able to complete that, then by coming Friday, I will try to get the questions up. So it will have all these questions will come up about the Verilog, about writing test bench, waveform. Whatever you're looking to the waveform, these kind of questions will come until now. Whatever Gopal has taught, from that will come. So I'll try to compile the questions and give it. Prepared.
Is on Saturday or Sunday, sir?
No, the question, it will be an objective question, so you will be taking it up on the LMS only.
Yeah, on Saturday or Sunday, sir, we can take any day.
I think usually in LMS you can take it at any time. Only the duration matters. Like
okay, got it, sir. Yeah. From Thursday, Friday. Yeah. Because for Saturday we will be free and we can take it Saturday, Sunday.
Yeah.
Okay, sir. Thank you.
Why I'm putting on Thursday, Friday is you should be get practice. Saturday, Sunday, coming Saturday, Sunday. So before that, you get practice, and once your practice is done, once you start answering the questions, then that will be the right time.
Sure, sir.
Okay. You're able to see my screen?
Yes, sir.
Okay.
Yes, sir.
Okay. So what we'll do is go with Mealy and Moore state machines. Okay, so there are basically two models developed, two models. For representing the synchronous sequential circuits. One is the Moore circuit, second is the Mealy circuit. Okay, so what is the main difference between Moore and Mealy circuit? Is the main difference is basically only the way output is generated. That is a basic difference. So in Moore circuit, you will have your output will be the function of in Mealy, your output function will be the function of both present state and inputs. I'll tell you how does it like how does the circuit looks like. So your circuit will have one it will have an input in this next state, then this goes to memory, and then it goes to output logic. Your memory will have a clock. Then this goes as next to it here. So if you see here, so this is combinational logic. Let me highlight. So this is completely combinational logic. Oh, it's not visible. Yeah. So this is combinational logic. This is again combinational. This is going to be sequential. What does that mean? Can anyone tell?
Sequential because it has memory, sir. Right?
No. Yeah. So what does combinational means?
Sequential means depend upon the previous output.
Sequential is depend upon clock is.
No, actually, whatever you're saying are bits and pieces. It's right.
So combinational basically depends only on the current inputs.
Yes.
So once that input is given from the is given to the next state logic part, the output is then stored in the memory sequentially.
Exactly.
And
So
then,
yeah, please go ahead.
And then this output of the memory is given to two blocks. So in the output logic, next output logic, which is also a combination circuit, the output from the memory becomes its current inputs.
Yes. So
at the same time, this also goes back to the is given as feedback to the next state logic's input.
Yes. So here if you see this is going to act, this particular fellow is going to act as a next state, and this particular fellow, the output that is coming out from your output pin is going to be a present state. Okay, so you will have output every time, but also one part of your output that comes before this combinational logic here. This goes from here, it goes back to your next state logic, and that goes as an input again. So let's see one small circuit. With that circuit, I think this block diagram we will be able to understand it better. Okay, so let me put two flip-flops. What is a flip-flop? Is it a combinational or a sequential element?
Sequential.
Sequential.
Yes. So I have, say, this is the DA of the flip-flop. This is a QA. Then this is QA bar. Here DB, QB, QB bar. Okay. So let me consider doing like this. So I have an AND gate. AND gate goes here, and I have A input. Hold on. Then you also have a clock signal in the flip-flop. So the clock. Then what do I do then here? This one, let me give it here. This one bringing out here. And so if you see here, let me mark in red. if you see here, I have two flip-flops. In that, the DA pin is fed is fed from the AND gate. Output of the AND gate is fed here, and I have another D flip-flop which is DB pin, which is getting input from an OR gate. My input signals are A and A bar are my input signals. Then my output. So these are my inputs and this is my output. Now, if you see this block diagram, yeah, if you see this block diagram, whatever I said here as the next state logic, output logic, and memory. If you see whatever I'm marking now here is this is the what is this?
Logic
And
combination.
Next state logic.
Good. So this is my next state logic. So this is my next state logic, and what about this?
Output logic.
Output logic.
Yeah, this is going to be my output logic, and the blue color part, whatever is there, no, that is going to be
Memory.
Okay. So here, if you see what I have drawn, is it a Mealy or Moe? To identify that, let's see what is the output here. So output, if you see, what is my output? Y is equal to OR of what?
Q bar B and QA.
Yeah. QB bar plus QA, correct?
Yes.
Now, yeah. Now, if you see this equation, does this equation have any component of input A? This one?
No.
No, right? So you go to the definition what I said here. Moe will have the output. Output will be the function of only present state. Mealy will be having output with a function of both present state and input.
Okay.
Now, what is this? Mealy or Moe? Guys?
Moe, right?
One more.
Mood state.
Guys, all are clear?
No, yeah, it's only present state it is dependent, right? Not on the input state.
Yeah, this doesn't have any function. This output is not having any functions, any expression stating this A, right? There's nothing A is coming out. Only it is dependent on the output and the QA and QB. That's all. Correct.
But QA is not related to the input, sir.
So this QA is a representation of this flip flop, sir. QB is representing this flip flop.
Right.
So what you see, the output, whatever is coming, is a function of QA and QB only.
Present state only.
Yes, only the present state.
Okay.
Now if I'm changing the circuit, say like this. I'm pulling. Let's take another color. So I'm pulling this A and giving it as another input here to this OR gate. Okay. I mean, is it clear? I'm just scribbled it, but is it clear? I'm just pulling this A.
Yeah.
Yeah. So what I'm doing is I'm going to now what my output equation looks like. Y is equal to
A plus Q by bar plus QA.
Yes. So your output is a function of A now. It is function of A. I mean present state and input. Correct.
Yes.
So this is going to be what?
Mealy or Mealy.
Mealy. Yeah, this is going to be Moe. Please, I mean, it will be initially it will be a little bit confusing only to remember which is Moe and Mealy, but it will get used to you very soon. So it will not take much time. You just remember Moe means only present state. Mealy means present state as input. That's all.
So by present state, you mean like what is currently stored in the memory? Is that what you take it as state?
Yes.
I have the same
Your output will always come. Whatever is there in the present state, it will come. Even though you are feeding the present state to the next state. See, if you are here, you are doing it. You are able to see. Or maybe I'll take one. Wait. See here, you are. 1 minute. So I mean, let me tell it like this way. So you have the QB, right? QB is going, and again it is going back to the AND gate, and again it is going to the output of the AND gate is going to the DA pin. So the output from the second flip flop is going as input to the first flip flop also. But still, the output here for Moe will be only the function of present state only, QA and QB only.
Why would we consider that? Because there's a dependency there, right, on the input somehow. It's going to input on DA pin.
Yeah. So what does that mean?
I mean, so still there is a. I mean, the output from QB, right? You are joining it again with the DA, correct? To the
so
A, correct?
what does this mean, sir? Means it is like here the output of the memory you are giving back to the input.
Correct. Output of the memory is given back to the input.
Yeah.
So, okay. That does not create a dependency on the. I mean, it cannot be considered. It depends on the input, is what you are saying. The present state.
Yeah. It doesn't depend on the input. That's
Yes.
all.
Yeah. That's it. We need to consider like that.
Yeah.
And when you say present state, right? So these both like the QA and the QB, right? Both these are considered as part of the present state, right?
Yes. So these two flip flops are considered as part of the present state.
Present state, two flip flops. Yes, that was the thing.
Yeah.
Thank you.
Okay. So, so this is done. So what we will do is we will take one small example. Some two examples we will see. Okay. Anybody is aware of what is ones complement? Ones complement is basically in a digital operation you do addition, subtraction, like that. You have to do complementary operation also. Anybody knows what is ones complement is?
So it is like opposite.
Anyone, please. Anyone. Sorry, anyone. Yeah, go ahead.
So it's basically the inversion of the bit when you do ones complement.
Yeah. So people who doesn't know, if I have say this representation 10110, if I do a ones complement operation, that means it will become 1. This 1 will become 0. This 0 will become 1 like that. So it becomes 0 1 0 0 0 1. So this is the ones complement operation. So what we will do is we will create a Mealy machine. We'll create a Mealy. The first example is what we will do. 1 second. Yeah. Create a Mealy machine that produces the ones complement of any binary input, or you can say it as string. Okay, for any binary string. Okay, now let me consider as an example, I am taking 1 0 1 0 1. Now I am going to create a Mealy state machine. So I have the current state as, say, S1 is my current state. Now, if my input is going to be 1, so if my input is going to be 1, then my output is going to be 0. If my input is going to be 0, then my output is going to be 1. So in Mealy machine, you represent inputs and outputs on this arrow only. So this is my input and this is my output. So this is one simple small example just to tell you how do you represent only. But actually what we will do is we will take another serious example. What we will do, we will see if one small sequence. If that sequence is coming, then it has to print something. So so what was the problem statement will be is you construct a Mealy and Moore both machine that prints y whenever the sequence 0 1 the sequence 0 1 is found in any input binary string. Got it. So whenever that input binary string has 0 1, then my output should be printed as y. Okay. So if you see what all to solve this, what all inputs are there? In inputs you have 0 and 1. For what output should give, it should give y. I mean, I'm considering x and y. In that, y is the one that is my required output. Okay. So to do a Mealy state diagram, let me consider, since here you have to identify 0 0 1, right? So my initial state will be a, and if A state is getting an input 0, then it goes to my next state. It's like for the sequence 0 1, if I'm getting 0, that means I'm going to the next state B. If I'm getting an input as if I'm getting 0, it will go to B. If not, if it's getting 1, then I'll stay in this state itself. That means what? If I'm staying in this state itself, my output is, I mean, let's mark all the outputs later. I'm just for the ease of understanding, I'm just marking the input and going to the next state. So when my input is 0, I can go to the next state. When my input is 1, I will stay in the same state. Now I'm in state B. Here, if I'm getting an input 0, if I'm getting an input 0, if I'm getting an input 1, so it will complete my 0 1 sequence, then I'll go to my next state C. Now, after this, if I'm going to get an input 0, then I will, if I'm going, so now I'm going to get 0. That means I can expect another 1 or 0 after that, right? So now I will have to go to a state where it should help me in getting 1 for getting another 0 1 sequence. So from C, I will go to a state which is B. If it is 0, I'll go to B so that it gets 0, and then again, if I get 1, then I come back to C. Suppose if I'm getting 1, if I'm getting a 1, then I go to this initial state here. So now I'm going to mark all the outputs. When I'm getting the 0 1 sequence, then I should get an output y. So where I'm getting from here, I'm given 0 as from when I'm giving input 0, it is going to the next state. Then here it is going to next state when I'm giving 1. So I'm getting 0 1. So here only I'm going to get the output, which is going to be y. Rest all places it is going to be stay as x. Here, as I said, this is a Mealy machine, so we will be representing input here as this as input and this is as output. I hope this is clear. Anybody has any doubt here? Next, we will go to Moore.
So can you explain from C you joined B, right, with the input 0? Can you why C to B?
So C is a state where after here I have achieved my requirement. 0 and 1 has already arrived here.
Right.
Now after C where it should go, there is an after the 0 1 has come. Now if I am so I have 0 1 0 1 like that. So first 0 1 has already come. Well, now I am in state C. Now after it has come to C, there can be either a possibility of 0 or 1 again.
Correct.
Now if there is a possibility of 0, then after that there might be a possibility of 1. Which is my sequence again.
Right.
So if you see, if why I'm connecting it to B is here, if I connect it to B, then I can get a 1 and come back to the state C and get my output y. So for the 0, I'm going to B, correct?
Yes.
And after that, if I'm getting 1, then I go to C, correct?
Right.
So what I'm getting 0 and 1. 0 1 is my sequence again, correct?
Right.
So that's why I connected it to B.
Okay.
Now if I'm going instead of the 0, if I'm going to get 1, 0 1, and if I'm going to get 1.
Right.
1 means it is not part of my sequence again. This is going to be something new for me.
That's correct. Now sequence is 0 1. Our sequence is 0 1. Yeah.
0 1. If I'm getting a 1 here, then I'm going to the initial state.
Got it. So which joins to A back again. Yeah.
Yes.
Okay. So that 0 1 sequence continues from there.
Continues. Yes.
Yeah. Okay. Thanks, sir.
Sir, I have a doubt here.
Yeah.
So whatever I understand, in any of the conditions, signal will not move forward towards C. After B, signal will not go to C, because whenever you put the 1 at A, then it will be coming. It will be in the present state with A. But if it is 0, then only it will go into B, and again it is staying at the B. So how it will be going? My understanding, the signal will not move forward across B.
After B, you're saying the signal will not move forward.
Yes.
Why?
Why? How it will go? If it is 1, then it will stay here at A. If it is 0, then it will be going to B, and it will stay at B, because 0 it will be referring this. It will be reversing there. It will be present state for the B.
No. I think you have misunderstood it. So let me tell you once again. See, we are going to identify 0 1 sequence. So A is my current state. Okay. Now, when I'm in state A, if I'm getting a 0 as my input, then then if I'm getting 0 as my input, then I can go to my next state, considering that, okay, this is a valid thing for my sequence. Okay, my sequence is 0, 1, so I will go to my next state B. In case if I'm not getting 0, if I'm getting 1 here, then I will stay in A itself, because it is not a good state for me to move forward, because that is not part of my sequence. Now for B, now I'm in B. Here in B, if I'm getting 1 again, then it is 0, 1 is my sequence, which is going to come. Then I will go to the next state C. If it is not 1, then if it is going to be 0, then I will stay in the state itself. Okay, let me consider one small example here itself. Okay.
Then B input will be separate. There will be no sequential flow. It will be parallel flow. A and B.
No, it is sequential. Let me give you an example. Okay, see, let me consider 0, 1, 1, 0 as an example. Okay, now my input is 0. Okay, when my input is 0, what will be my I have to get a 0, 1 sequence. When my input is 0, my output is X. Now after that I'm going to pass 1. So when my input is 1, my output is going to be Y, because I have got my 0, 1 sequence. Next, when I'm going to go to C. Now the state is C. Okay, now here when my input is 1, I'm going back to A, so my output is going to be X. Now when my input is 0, if my input is 0, then I'm going to B. Here also my output is going to be X. So once excuse me. So once I'm detecting my 0, 1 sequence, at that point only you are getting the corresponding Y output. Otherwise it stays in X only. I hope it's clear now.
So in the second one, next to measurement means whenever input is 1 at what point? At which point? At A or B?
At B.
Okay. Now then, if
we have finished A.
At B, then it is correct. But input is we are getting through A to B. That's why it is confusing.
No, it's from B. It's not from A.
Okay. Then it is correct, sir.
Yeah. So this is the Mealy representation. Let's quickly represent the same thing in Moore. So Moore again. You have state A. When the input is 0, it goes to the next state B. 0. When the input is 1, it goes to the next state C. Then when the input is 0, it goes back to B. It is 1, it goes back to here. If it is again it is 1, it stays here. If it is 0, it stays here. Yeah. Here, how do you represent this? Here you will represent in the outputs inside the state only. So where you are getting the 0, 1 sequences, you are getting the 0, 1 sequence at C state. So you represent Y here. Rest place you will put as output as X. So consider an example, the same example. 0, 1, 1, 0. If you see here, so when my input is 0, I go to B. So again it is X here. When my input is 1, I go to C. So my output is Y. Then again it goes to, when my input is 1, again it goes to A. So X, again here X. So you're getting a sequence here 0, 1. It's just the way of representation. Your output is represented inside the state. Here the output is represented along with the inputs. Yeah, that's all.
0, 1 sequence allows the movement to the next state, right? If it follows the sequence, the whole goal is there, right?
Yeah. So if we can consider the sequence to be still more also, in that try to find out wherever 0, 1 is there, at that time only Y will come.
Yes.
So this machine goes in. So from this only, what we will do is we will write a Verilog code out of this, okay? And that Verilog code gets translated to a hardware that will become like a sequence detector. So sequence detector is like we'll find it various industry applications, like in huge industries and all, where in industry where automation is there, where series of things are on a conveyor belt. How many of them are in particular sequence? How many items are in particular sequence? That has to be identified. Those kind of digital circuits can be designed, as well as there could be a counter, like counter example that we have seen. That also in airports and all, if you see the conveyor belts that carries your luggage, how many counts of luggage the packages are going inside the flight, that needs to be counted, right? So those things can be counted, those logics can be implemented using that. So this is like this, whatever you are designing, right, it gets its application on place.
One question, sir. So in this Moore one, the memory is not coming into picture here, sir?
It is. So what about the states that we are talking, A, B, C, R? Whenever it is whenever it is going from A to B, that means it is going to next state. Okay.
Right.
If it is going to be in the current state, that is the present state, it stays in 1. If it is 1, it is going to stay in the current state.
Okay, that the same, it is reflecting back to the same circle, right?
Yeah, that is the present state. Yeah.
Oh, then I mean both looks like the memory ones only, right?
Yeah, both of them has it. So here the difference is this only. The difference is, as I said, right, this will be Moore will be only having the present state. The output will be depend on the present state. Mealy will have its own with the input also, with the current state input also it will have.
Okay. I mean, can you go to the below diagram? So the first one is, what is the difference between these two? I couldn't get. Both are looking same for me. Mealy and Moore.
Okay. See, what did I say here? Mealy. Let's say Mealy. Mealy will have inputs. Depends on input, right?
Input. Yes,
right?
yes.
So it's above one Mealy. So here, see, it is dependent on input. Representation, whatever you have done. Okay. The output is dependent. On input. That is how you are represented.
Right.
Right?
Oh yeah.
Yeah. But Moore, the output is there inside the states itself. The output is not dependent on input. The output is dependent on in which state it is there. Only the state is dependent.
Okay.
That's why you are representing the output inside the state.
Okay. There is a difference in X inside and X outside.
Yeah.
I thought it is same, just you have written like.
No.
Instead of writing outside. Okay. There are a lot of.
No. This is not like a simple game. No, it's a concept.
Yeah, that's correct.
Okay. Then. Fine. Let's wind off today. I got a meeting after this, so I can extend also. Let's wind off now. Tomorrow we will meet. We'll start to explore a few more concepts. I have something tomorrow. Let's see. Okay, let's take one more minute. Any doubts? Any clarification?
Sir, some PLCs and ICS, DCS, those are designed using the similar Verilog code, or how it is?
Yeah, wherever you need to have a little bit of automation is required, then the digital components come into picture. Okay, but actually, this is how it started. This is how the digital design started. But now it is in a different state. Now you don't need one small counter chip to come and count things. Right now it is all embedded in one SoC, one system on chip processor itself. Then everything is happening in one SoC. All applications are happening.
So in current scenario, how we are doing the coding? In the similar fashion, we are doing coding, or some graphical way we are doing coding?
No, we are doing hands-on coding only. There is nothing, no magic is happening.
In graphical way, some drag and drop, then do the code appears automatically. In this,
no. That way you can't write an optimized code. That way you can't write your optimized code, and that will not behave. You have a lot of things.
In some systems, some low code, no code system in the AI, if you just drag and drop, the code SQL code generated automatically, and that is optimized only.
To my experience, that is not an optimal code, Vishwajit. So to write a code, a serious processor, if you want to design, it is not going to happen that way. Because no AI tool has come up to design a hardware. For software, you can do all magics. For hardware, for every cycle, you should know what is happening, and you should be aware that if that hardware is synchronized with respect to the input, whenever there's an input, it has to get synchronized with the clock. So there should be some synchronization logic that has to be there. Those things that are hard, AI will not be able to handle it.
Okay. So one more question today.
Yeah,
so in the lithography machines, whenever we use the lithography machines for the high complex transistors or whatever chips, so same way they used to code in the same way.
No, that is there. Nothing coding is there. No, there it is going to be. They are going to just they are going to grow the layout only. No? It's just silicon growing there in lithography. There is nothing coding. So coding is our part. So
Pre-requisite coding is there. Or?
Yes, that's what we are doing now. Once we have written the code, once we have written the code, now we will go to the next step. We are going towards that photolithography process only.
Okay, right. Okay, thank you, sir.
Thank you. I think let's wind up. That's all. Thank you so much.
Thank you very much, sir.
Thank you.
Thank you, sir. Thank you.
Okay, we'll get started.